Okay, so today, all right, for your attention. So today we're going to do two things. One is we'll continue talk about indeterminate problem, that is indeterminate shaft, and then we'll leave some time if you have questions about chapter one or maybe chapter two, for the coming up exam. All right. Okay. So last time we already started talking about indeterminate problems for shaft. And we went through one example, that is, if you have a shaft that's fixed between two walls, two rigid walls, and then in the middle somewhere you apply a torque, right? Or you can actually apply two torques in the middle, and that is an indeterminate problem. And we kind of went through the method to solve it. In a nutshell, that is the Fed.com. So we use the Fed.com again, right? Okay, so quickly, let me ask you one question here. Okay, what if we have a shaft like the one we just covered last time? Okay, so you have here a shaft. Now, if we apply two loads here, so you have a T2 here, and then you have a T1 here. This is our known load, right? So you can call it, if you want to distinguish, we'll call it TB here, TC here. It's just two loads. So you have A, B, C, D, four locations. Okay, so for this shaft, fixed between two walls, and there are two loads there. They're all known. One is 10, one is 20. Okay, is this determinate or indeterminate? It's indeterminate. Okay. In other words, it doesn't matter how many load do you have. You know the load or you don't know the load. It always doesn't matter in terms of determinate or indeterminate. What matters to determinate or indeterminate is how many equations do you have, right? Basically, how many reactions do you have? Like this one, both end fixed. So you have two reactions, and you can only find one by equation of equilibrium. That's why it's indeterminate. Has nothing to do with how many loads do you have there, right? So that's a concept we need to quickly clear up. Remember last chapter, I'll give you a quiz. Okay, so let me draw the structure here. So you have this structure. Okay, so this is the ceiling here, the floor. So we apply load here, right? And then you apply another load here. Okay, so is this one determinate or indeterminate structure? It's determinate because there are only one unknown reaction, right? That's from the bottom there. So doesn't matter how many load you apply there. You have only one reaction, and that we have enough equation of equilibrium we can determine. So therefore, it's always determinate. All right. Okay, so today let's go over another example for indeterminate shaft. Okay. So again, the approach will be the Fed.com part. Right? Okay, so what we have here is a shaft that composed of two parts. One is a rigid cylinder, a mandrel inside. Another is a shell, a cylinder outside. So these two can be different materials and different dimension, of course. Right? And if you cut the cross section, that's what it looks like here on the right. You see the cross section view. Okay. So for this one, it's actually at the end there is a rigid plate here. So you apply a torque T. So let's call this one TB here. So this is TB. You apply here. All right. So the question is, when I apply this torque there, how much rotation are you going to get? So we know the load. We want to find out the deformation. Okay. So now the first question is, Is this a determinate or indeterminate structure? Why is determinate? How many unknowns do you have? Reactions? 1 or 2? 2. Why you say 2? Because you have a solid bar, right? Solid shaft. The mantle inside going to get a reaction from the wall. And then you have the shell, the cylinder, going to have a reaction from the wall. Therefore, you have 2 unknowns. Right? All right. So actually, we can delay this question a little bit. Let's go through the Fed.com. Right? If it's determinate, you don't need the com part. You just need the Fed part. You can solve it. Right? So let's lay out this, see if we can solve it without the com part. All right. So the free body diagram first. You have to do this anyway, right? Okay, the free body diagram. How do you draw the free body diagram? You need to select a body, a free body, or in this case, cut a free body, right? So you need to make a cut. All right? As we said, you can cut anywhere in the middle. So I can just cut here. Right? So if I cut here, that's what I get. So I have this part. This is the end plate. And then here I have the shell part. And then this is the mandrel part. And then this is the shell cylinder part. Okay. What's the load on this free body? You have load TB here. Right? Okay, reaction. When you cut, the cylinder is going to have a reaction. Right? That's a torque. And we call it internal torque. Just remind you, this is local here in this segment. Okay, so we need to use a label. What do you want to call it? T bar, right? Okay, so T bar. T bar. Okay, then the other one is the cylinder outside. So that's the cylinder. There will be an action reaction if you cut it out. Okay, so you're going to have another torque here. Right? Let's say called T tube. Okay, what about this side? Here. This is one cylinder, right? So we're trying to label the whole cylinder. You're going to have a reaction moment or the torque. So therefore, the TT is for the whole thing. In other words, you don't need to label another one at the bottom. That can get you confused. You think there are maybe 2 of them. There are actually only 1. This one is like a hollow cylinder. So the torque is applying on the whole thing. Right? The way I draw this, because I kind of like a cut this way, a longitudinal cut. Look at the cross section, longitudinal section. So that's why you kind of show up 2 little end there. But actually, remember, it's one thing. It's actually, you have a torque applying here, right? The cylinder part. So this will be the T bar. And then you have another torque applying here. So this is the T tube. So you have only 2, right? Okay, so to help you prevent double counting, you just draw on one side will be enough. Yeah.
Is there ever going to be a case where the torque isn't symmetric?
What do you mean symmetric? When you rotate a cylinder, you're going to apply a torque there on the cross section.
Yeah.
So the torque it will be this way. So there's no symmetry. Hold on.
It's from the center, right? Is there ever going to be a
Well,
case where it's not coming from the center?
how you interpret a torque? A torque is basically a moment that you apply, generate a twist, right, along this direction. That you call a torque this way. So you're applying here. So there's no center or no center issue there. It's just they say this torque is applying on the cylinder. Right? As a cylinder, so the whole cylinder, you're applying a total torque. All right. Okay, so that's a free body diagram. And I'll say it's complete. Right? I label all the load. I label all the reactions. All right. So now next will be equation of equilibrium. Okay, for this free body diagram, how can you write the equation of equilibrium? All the moment added together equals 0. Right? Okay, so you have one independent equation because everything is in one direction. So you have only one equation. Okay, so we have all the moment in the axial direction equals 0. In other words, all the torque add together equals 0. Okay, so translate that. Negative TT, negative T bar, right? Then plus the TB equals 0. Okay. Any other equations you can write? Sigma fx equals 0. No force there, so automatically 0. Sigma fy equals 0. No force there, all equals 0. Right? Sigma moment in the y direction, sigma moment in the z direction, there's nothing there, so they all automatically satisfy. So the only non-zero equation is this one. So now you see one equation, two unknowns. So that conform is indeterminate, right? Okay, so once we know it's indeterminate, now we know we need the compatibility part. So we need to follow the fed.com. You cannot stop just at the fed part. You have to add the compatibility part. All right, so now the deformation part. Which parts are deforming? And what kind of deformation you have? The bar and the tube, they are twisting. So you're going to have two angles, phi 1 or phi bar. That is supposed to be T bar, right? Times length of the bar, G of the bar, and then IP of the bar. Right? So this will be one line here. What's the P? There's no P here. Oh, IP. What's the IP? It's the polar moment inertia, right? That stands for the polar. All right. Okay, so that's the bar. What about the tube? What's for the tube? Should that be T tube, right? Times the length of the tube, then the material of the tube, and then the IP of the tube, right? Okay, we know the length. Let's say here, 500 millimeter, right? We know the material, G. And then we know their size. It's giving, okay, it's giving all the diameters. So the label there, somehow the number was missing there, but we know it, right? So the only thing you don't know is the T bar and the T tube. Okay, so but we have two unknowns, so we cannot stop here. We have to use the compatibility. Okay, now what's the compatibility? Look at this thing. How does it deform? How does the phi 1 and phi 2, or the phi tube and the phi bar, how are they related? Without break apart of the system, right? Okay, when you twist this end, the end plate will rotate. Okay, when the end plate, let's say, rotate 1 degree, how much does the bar rotate? 1 degree. How much does the tube rotate? 1 degree. Otherwise, they will break apart. So therefore, the compatibility actually, in this case, is easier than chapter 2. That is, the phi bar will equal to the phi tube. And that is actually the angle you're looking for. Right? So that's the additional equation that we can add to the equation of equilibrium. And that additional equation will make this possible to solve it. Okay, now quickly, let's solve it together. I think this is easy, maybe too easy, right? A problem to solve. I mean, mathematically, right? Okay, you have one equation is here. So let me change the color of the pen. So we have this one equation. Oh, let me change. Okay, so this is equation 1. Now, this is the second set of equation. This is the third set of equation. Okay, how do you solve these 4 equations together to get the answer phi 0? You can eliminate anything right? Find the answer and then take it back, find whatever you're looking for. All right? Okay, so which one you want to combine to eliminate first? Substitute 2 with the 3. Okay, can we do that? All right, let's do it. So here, this one equals to T bar, then L, G, the bar, and then the IP of the bar, right? That will equal to T tube, L of the tube, and then G of the tube, and then IP of the tube. Okay, L cancel out. You know all the other parameters except the two T's, right? So this gives you a relation between T bar and T tube. So for example, I can get the T bar equals to G bar over G tube, and then the IP bar over IP bar, and then IP of the tube, then times T tube, right? Okay. Now give you a relation between the two torques. Now can we take this back to equation 1 and find the answer? All right. So we don't have to do it here, right? So you can finish it. And once you know the T bar, T tube, now can you calculate the phi 0? Yeah, you can just put it back to equation 2, and then you get the answer. All right. Okay, any questions here about the process? So my suggestion for if you see an indeterminate problem, just follow these steps. Do the free body diagram, equation of equilibrium, deformation equations, and then compatibility. And then just solve it. Make sure you lay out all the equations, right? Then I know that you understand, you know how to solve it, right? And so for the exam, for example, if you lay out all these equations, I know you know how to solve it, you will get most of the credit. And as to when you now you won't get 100 because solve it, get a solution. That's the important part as well, but that's a small part. If you get the wrong answer, the number wrong, but you know the step how to do it, you should get most of the credit. I give partial credit. All right. So make sure you lay out the equation. Don't just directly put the number because you just put the number there. If the number is wrong, I will take 100% point off because that's only CRC. It's wrong, right? If you lay out the equation, show how are you solving. Because for us, it's very important to see you know the process, you know how to do it. The how to is more important than the answer itself. Of course, later on when you go to work, right? The correct answer, that's the critical thing. They don't care. Your boss may don't care how you get it, but you get the correct answer, they can select the correct material, right? That's the most important one. Okay, yeah. Okay, good question. It will be somewhere 2 to 4. You should be able to finish it in 1 hour, in 50 minutes, right? So also for the exam, I have a meeting come up, a department meeting come up right away, so I need to leave on time. But if you can come a few minutes early, we can start a few minutes early. All right, say we can start 5-10 minutes early. 4:30. You can come in, let's say 1:30 or 1:40, right? And I'll try to be here by, at least we can be here by 1:50. So we can start a few minutes early. All right. All right.
The syllabus mentions a one-page formula sheet. Is that front, back, or front?
Okay, so the formula sheet, I'm going to provide it. All right. We used to have you all bring, but then people just bring the wrong equations, wrong formula, or put lots of homework on the formula sheet. So therefore, we're going to provide, you don't bring any formula sheet. We'll give you a copy. All right. Yeah.
Is the formula sheet going to be made available to us before the day of the exam?
Yes, you can see, actually it's already there. It's basically the summary slide we had in the summary part. Remember we had that summary class, right? So it's basically the same thing. I'll give you the basic formula sheet. Right. So you need to get familiar with it. All the signs I use the same as textbook. So if they say sigma, don't ask me what's sigma, right? If I have this delta equals NL over EA, don't ask me what's A, what's the E there. I assume you should know it. This is like a reminder for you what's the actual equation format. Yeah.
Just make sure that's going to be over chapter 1 and 2, right?
Yes. Just chapter 1 and 2, no chapter 3. What we cover here will be our next exam. It won't be in Friday's one. All right. And actually, I believe in chapter 1 and 2, there are maybe 1 or 2 sections we not cover it at all. So you don't need that part. I remember there is one something like a the Gill mechanism, right? So we didn't really cover that. You don't have to spend a lot of time on that. All right. Okay. All right. Any other questions? Since we already talked about the exam. Right. So when you come to the room there, we have a big room. So just sitting apart from your next seat neighbor. Okay, you need at least one empty seat away from your next person. All right. This way, if you sit already that, then we don't need to spend time to rearrange your seat to get us started quicker. All right. And also, there are a big issue about student cheating now. There are more cheating occurring. So I'm trying to be more friendly by take some preventive measure. Instead of I caught you, cheating, I have to report it. If I get it, I have to report it, right? But I will try to do things preventive, basically by sitting you apart. Also, there will be no bathroom breaks because people go to bathroom, just call a friend or somehow. That happens, Supposed to be just go to the restroom, you use it there, right? Only 50 minutes, so beginning, if you need to go, just go at the beginning, all right? And then another issue is cell phone, right? I know you can search a picture or things. I can tell you my problems won't be from the textbook. You don't need to spend the time to search it, all right? So it's not from the textbook or another one. I just made up all the problems, all right? Also, if you need a calculator, brain calculator, don't hold a phone there. Say, oh, I need a phone use as a calculator. I won't buy that, all right? If you're holding a phone, then that's evidence of your cheating. All right. So put your phone away, out of reach. You have a bag. Put it in the bag, right? Turn it off. Don't put it on your pocket or anywhere. Keep the phone away from you. And if you don't have anywhere to keep it, you can bring it here. I will just keep it for you, and then you can get it back. All right. Okay. So that's more logistic issue. Any technical questions about the content that we're covering, or any homework problem you feel challenging, you want to go over here, we can spend a little bit of time here as well. Yeah.
It's going to be the same room for the internet lecture, right? Same room, same time?
It will be same time, but the room is not here. It's in a different building. I email everyone that, so it will be FLN, I think 2.312 or 2 something 12, right? Okay. Yeah.
Formula sheet was on the fly.
Formula sheet, that's the 2 slides that summarize chapter 1 and chapter 2. Yeah. I'm sorry?
The formula sheet, are you printing it for us that day?
Yeah, I'm going to bring one for you. It's in that slide. If you don't see it, I can post it again. It's the same thing. What we have, I already showed you, so that's all right. Okay, any other questions or problems from chapter 2?
Would you mind doing like a misfit problem?
What's that?
Like a misfit example?
A misfit, okay. All right, we can go over any other questions. If not, let's go over one misfit problem. And then, or thermal is related, right? Okay, we can go over that. All right. Okay, let's move to a new page so we can go over misfit. Okay, so, there are there are different type of misfit. One is you have a cylinder, right? It will be short there, and then you can have a misfit. Or you can have, I think you can have another type that will be, let's say this one here, and okay, so there's a misfit here, or there's a misfit here, all right? So which one you want to go over? The wires? Okay. All right, so we go over the second one. Then it's your homework to go over the first one, right? So if you have a load here, for example, right? Remember we talked about now back to chapter 2. So it's force, no movement, right? It's force now. Okay, so this one, let's say we have a force here. All right. Okay, any other misfit situation? Or you can actually have this one, I think. You can have this bar here, this bar here. Somehow this bar is short by a distance, right? Then you have a load here. So this will misfit delta here. Okay, let's go over which one you said, this one, right? Okay, one on the test. No one of them will be on the test. Okay. I can tell you no one of them will be on it, not on. Otherwise, I won't go over it. All right. But they're all helpful for the test, I can tell you, right? Okay, so let's go over this one. All right, say if we have a load, we know the length. Okay, what's known? What's the question? Do we need to ask question? Figure out the load you can apply there, or figure out the deformation you have there. You want to review the content, or you want to make the argument? Okay, let's say we want to find out deformation or the load, limit or load. Deformation. Okay, so we want to find out how much, let's say, this point going to move, delta here, right? If you apply load, how much is going to move? All right. Okay, first, this is determinate problem or indeterminate problem? By doing lots of homework now, you should say now it's indeterminate. Because you have two bars, you're going to have N1 here, N2 here, right? If you draw the free body diagram, so you're going to have load P here, then the N2 here, and then you have N1 here. And then you have, what's here? You're going to have what? Reaction force. So you can have a Ry here. Now, 3 unknown, 2 equations. So that's why it's indeterminate. Right? Okay, so what's the equation of equilibrium? Sigma moment about point A equals 0. Where's A? Here. Okay, so this point B, this point C, and this point D. Okay, so you're going to have N1 times this distance, AB, right? And then plus N2 times AEC. Then minus P times AD equals 0. By that I mean the length, right? Or the AB means the length of the AB segment. Okay, so one equation, 2 unknowns, indeterminate. All right, so that's the F part, the E part. Now the D part. Deformation. Delta 1, bar 1 going to elongate. Okay, good question. Can you add another equation, use the sigma Fy equals 0? Yes, you can, but that doesn't help. Okay, why? We can just write here. Sigma Fy equals 0. Now you have N1 plus N2 minus P minus Ry equals 0. You have one more equation, but there is another unknown coming in now. So it doesn't help. And we don't care about Ry. Right? I didn't ask you, so you can just ignore it and use the moment. All right. All right, so the deformation. What's the delta 1? I think we already went through an example similar to this, right? N1, H1, then EA. Or maybe this will be different. And then delta 2 will be N2, H2, E2, A2. Now, what's the compatibility? Look at the picture. Look at the setting of the problem. Okay. The compatibility is the equation about what? About the delta, the elongations, the deformations, right? So in this case, you have delta 1, delta 2, two deformations. So what's the relation between delta 1 and delta 2? That's basically the compatibility. Okay, what's the relation between delta 1 and delta 2 in this case? Okay, let me draw another cartoon. Actually, I highly recommend you draw a cartoon that will help you find out the relation. Okay, hold on a second. So originally you have the bar here, right? I mean the rigid beam here. Then when deformed, this is a pin support, so this point not move. And the other part going to move down. So you have a straight line. It will move to this new dotted line position. So therefore, this part, this will be the delta 1. You start from here to this end here, delta 1. Now, this bar was originally here, right? But the other bar originally is here. It's only in here. So what's delta 2?
That would be, I think you get that. It should be delta 2 at the end.
Delta, okay, yeah, this is the 2. Yeah, thank you. So this is the delta 2. Now, where's delta 1?
Well, it depends on what A, B, and what AC are.
What's delta 1? Okay, when you write this equation, what's delta 1 mean? It's the elongation of bar 1, right? Elongation of that bar. Okay, this bar originally ended here. Now, how much it elongate? It must move to here to meet this rigid beam to move there, right? So therefore, this is the delta 1. What I'm drawing here is delta 1. So this part is delta 1, right? Now, where is the capital delta, the defect? It's this part, right? Okay, is it too late? You have a question?
I just wanted to don't take into account the misfit on the delta 1.
Okay, yeah, when you calculate delta 1, do you need to count that delta here? I would say yes. Okay, but do you have to count it here? I say no. The reason is, how is delta compared to your H1? You have 1 meter long, this 1 millimeter gap. So for the value, it doesn't affect at all. It's maybe 1 of a thousandth of it. So you can ignore it there. If you want to put it here, that's perfectly fine. It just, calculation-wise, you just punch more number there. But if you actually go through this process solving, you'll find counted here or without counted here, almost no effect. So make it easier, you don't need to count it here. All right. Okay, now back to the compatibility part. What's the compatibility equation in this case? How is delta 1 related to delta 2? That's basically the question. What's the relation between delta 1 and delta 2?
I don't know my lengths or my angles, so.
You know what? You know the length, right? You know this part. This is the AB. This ABC, right? So we know all the lengths. Okay, so AB side of angle. So AB length, right? Divide. Which one you want to divide? Proportional, right? Divide, okay, AC length. Okay, this ratio equal to what? To the ratio of this side. So that will be, okay, what's this side for the B point? Is this side delta 1? minus delta, right? So delta 1 minus delta, that's this side, here on this side, right? So I mean basically, let me use a black pen, say, here, it's basically this part, if I can draw here. This portion, this is the side, versus delta 2. What? Why you add it? Because you say for triangle, they're similar. So the ratio of this side should be the ratio of this side. That's what I'm writing here. That's why I minus delta here. Because the delta 1 is the elongation, and that's not the whole side. It's more than the side. It's actually, you pull an extra amount. Right? Yeah.
Why do you include the delta, the big delta there and not maybe the delta 1?
Okay. The question is why you can ignore the delta in this equation. You don't ignore the delta in this one. The reason is, in the first one, actually you should include it everywhere, right? To be accurate, you need to include it everywhere. However, for this, the first one, it's 1/1000th of the total, so you can ignore it. Now, for this equation here, these two are comparable. So you cannot ignore it. This one may be 1 millimeter, this one may be 1.5 millimeter or 2 millimeter. So they're the same level. So you cannot ignore it. That's the explanation. Okay. Or you can think the other way. Okay. If you ignore everywhere, then it doesn't show up anywhere. So you won't find its effect. Then you ignore all the effects, so you won't find the answer. Right? Because you ignore it everywhere. You can always ignore it everywhere. So just, oh, I don't count that mini tiny defect. So you don't get the answer. You ignore it. But the question here is, oh, I want to see the effect. So you have to include it. So you want 100% accurate, you include it both places. In the test, you can include in only one place or two places. Either way will be fine. But you cannot ignore it because I'm asking for it. How can you ignore it? You don't give me an answer. Right? For the actual real problem, when you are dealing in your work, oftentimes, oh, I say this is a tiny effect, small. I can ignore it. It will be okay. Okay, unless you want to check on that effect, then you have to find out how small it is. Because you don't know in advance how small the effect is. Until you find out, and then you know, oh, this is small, so later on, I can ignore it. Okay. So in the test, if I give you a defect, you need to include it. Include one location or two locations, it's up to you. Either way, it will be fine. And your answer will both be okay. All right. Okay, now we have this compatibility. Now can we solve it? Find out what we're looking for. We're looking for delta 0. We're not looking for delta 1, delta 2. We're looking for delta 0. That is the displacement of this end here. But they're proportional. Once you know delta 1, delta 2, you can find this one. Right? So when you talk about defect, what's the effect of this defect in the process? It is this part. It's affecting the compatibility part. Right? Equation of equilibrium remain the same. Free body diagram remain the same. Right? Deformation equation, it pretty much you can remain the same because you can always ignore it here, right? So it's pretty much the same. The only part that affected by the defect or thermal stress is the compatibility part. So make it easy. You clear. Oh, only the compatibility equation, I need to consider the defect or the thermal stress. Right? And one direct conclusion from this is, if it's a determinant problem, what? Then it doesn't matter at all. So in a determinant structure, there won't be thermal stress or defect causing stress. Only in the indeterminate problem, you're going to have this effect. All right. Okay, any questions about this one, this example? All right, any other questions? Yeah.
I noticed on the formula sheet, you didn't add the temperature formula, like the alpha.
Okay. Good point. I'll add it in case you need it. That's the equation we learned from physics, so that's not the purpose of test. So it's provided. All right. Can you send me an email? Remind me to add it? All right. Thank you. All right. Any other questions? If not, actually, we can dismiss a few minutes. Yes. Yeah.